12.2 Day 4, Example 1d. Again, we're going to evaluate the limit, but unlike the first couple parts of Example 1, parts A, B, and C, we're not taking positive or negative infinity and plugging it into a polynomial. This time what we're doing is we're plugging it into a rational function. We have a polynomial on the top and a polynomial on the bottom of our fraction. And when we do that substitution, we need to do that a little bit differently than the process for polynomials. Again, there's an idea behind this involving infinity that I want to talk about first before we plug in some numbers. So I'm just going to do a little scratch work off to the side here. It's not part of the problem. I'm just going to erase this in a minute, but I want you to think about this. I want you to think about a fraction. In this case, let's talk about a half. If you were to take a look at a half and you evaluated that as a decimal, that's 0.5 or 0.5. And what I want to talk about is I want to talk about what happens when we get this bottom number to keep getting bigger and bigger. So let's talk about a fourth for a second. Let's make that bottom number a little bit bigger, keeping the top number the same. So 1 over 4, well, that is 0.25. Let's do that with a few more numbers. Let's do 1 over 10. As a decimal, 1/10 is 0.1, and let's do like 1 over 1,000. 1 over 1,000 would be 0.001. So here's what I want you to understand kind of from a math theory standpoint so that we can use this idea to do this limit. If you were to take a look at these four fractions that we have over here in red, the top stays the same the whole time, but what I want you to notice is as this bottom number increases, as the bottom number gets bigger and bigger and bigger, what happens to the decimals is they keep getting smaller and smaller and smaller. If we have a 2 in the bottom of our fraction, we end up with 0.5. With a 4 in the bottom, that decimal gets a little smaller. And as those denominators keep getting bigger and bigger and bigger, we end up with numbers that keep getting smaller and smaller and smaller. Last idea, what if we did something really, 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 really big? Like 1 over 1,000,000. Well, there is a decimal for that, but that's going to be a very, very, very small decimal, and it's really, really close to 0. 1/1,000,000th, that's really small. That's really, really close to 0. So this is the idea that we're going to be going through and using to do this problem. All right. In order for us to use that idea, what we're going to do is something a little weird, and it's going to make the problem look hideously long and big and gross, but it allows us to go through and you actually evaluate this limit. So what you want to do when you have a limit as x approaches infinity or negative infinity of a rational function, you want to take a look at the top and take a look at the bottom and look at all of your x's. Look and find wherever your largest power of x is. In this case, in the top we have an x to the third, in the bottom there's nothing bigger. There's an x to the third actually top and bottom. So the largest power of x either in the top or in the bottom for this problem happens to be an x to the third power. What we're going to do next is kind of a weird step. What we're going to do is we are going to multiply this fraction by a really fancy number 1. If we're going to multiply by 1, we could multiply by 1, or we could multiply by 7 over 7, or we could multiply by negative 20 over negative 20. Our fancy number 1 that we're going to multiply by looks like this. The highest power of x that we had in this problem was an x to the third power. So what I'm going to do is I'm going to multiply this fraction by a fancy number 1. So whatever's here in the top and whatever's here in the bottom has to be the same. And what I'm going to choose to multiply the top and the bottom of this fraction by is 1 over whatever the highest power of x was. So our highest power of x in this problem is an x to the third. So I'm going to multiply top and bottom of this fraction by 1 over x to the third. That is just a fancy number 1. We have something divided by itself. So if I multiply this fraction by 1, it doesn't change the problem. It's going to change what it looks like, but it doesn't change our solution. So I'm going to take this 1 over x to the third, and I'm going to multiply that by all of these different values with our polynomial. So to make it look a little better, you wouldn't have to put these parentheses in there, but that's basically what we have. I'm going to take this 1 over x to the third, and I'm going to multiply it by each one of these 4 values in the top. So we would have, for this problem, the limit as x approaches negative infinity still out in front. And then for our fraction, if I take 5x to the third and I multiply that by 1 over x to the third, this x to the third here is going to go in the bottom of this fraction. It's going to go underneath this 5x to the third. So we have a 5x to the third, and then underneath it is going to be this x to the third. So it's going to look like this. That first term would be 5x to the third over an x to the third. And I want to do that with each one of these terms. So next we have a plus, and we have a 2x squared, and then we're going to put that x to the third underneath. Our next term is a minus x, and then we put the x to the third underneath. And then finally we have this plus 1 with that x to the third in the bottom. I want to do that with the bottom fraction also. So now I'm going to take this 1 over x to the third. That's going to put an x to the third underneath those 3 terms. So we'd have a 2x to the third over x to the third plus 3x over x to the third minus 2 over x to the third. That looks horrible. Compared to what we had originally, that does not look like that's going to allow us to get to a final answer. It just seems like a really stupid way to do the problem. But because we're plugging in either positive or negative infinity, in this case negative infinity, this is going to be the step that we want to do for our first step. Here's what happens next. We are ready to go through and just simplify each one of these fractions. In the original problem, I couldn't cancel anything out. But now that I have all of these individual fractions, I can. So for instance, if you take a look at this first fraction, we have 5x to the third over x to the third. There's no addition or subtraction in this fraction at all. So those x to the thirds, those are going to cancel out. So in my next step, I still haven't plugged in negative infinity yet. So I do need to keep this limit as x approaches negative infinity out in front. And now I'm going to reduce each one of these individual fractions. So 5x to the third over x to the third, those x to the thirds are going to cancel, and we just get the number 5. 2x squared over x. Well, 2 of the x's would cancel, so all of them would be gone in the top, but we'd have 1 left in the bottom. That's that quotient rule that we have. If you're dividing like bases, you subtract the exponents, but you can just think about it in terms of how they would cancel out. So the second term here in the top part of our big fraction, we have an x squared that would cancel top and bottom. So all of the x's are gone out of the top, and we would just have an x left in the bottom. That next fraction, we would have an x that would cancel, so there'd be nothing left in the top. That's going to give us a 1 there. And if we cancel one of those x's out, we would be left with an x squared in the bottom. And this last fraction, that does not reduce at all. I want to do that also with these 3 fractions in the bottom. So with our first fraction here, the x cubes cancel. That gives me a 2. Here we would end up with an x that cancels, so we would have a 3 over x squared, and then in that last fraction nothing cancels, so we would have a minus 2 over x cubed. Okay, still looks hideous, still looks worse than the original, but this is what we want to work towards before we plug in our infinity or negative infinity out in front. So in my next step, I don't need the limit anymore because I'm going to do direct substitution. I'm going to take negative infinity and I'm going to plug it in for all of these x's in our fraction. So that's going to give me this. We're going to have a 5, and then plugging negative infinity in here for this x, we would have plus 2 over negative infinity. In our next fraction, we would have minus 1 over a negative infinity squared. And then our last fraction would be 1 over negative infinity cubed. Plugging in negative infinity for the x's on the bottom, we would have 2 plus 3 over negative infinity squared minus 2 over negative infinity cubed. At the beginning of all of this, here is what we talked about. We said, I'm going to just sketch this out again kind of here at the bottom and then erase it, so don't write this down. We said that if we had 1/2, that's equal to 0.5. That's a pretty small number, but compared to like 1 over 1 million, that's a million. 1 over a million, this is very, very small. The bigger the number that's on the bottom, the closer this number gets to 0. So this is 0.5, but as you make this number on the bottom bigger and bigger and bigger, what happens is that this gets closer and closer to 0. And if you have 1 over infinity, that is even a bigger number in the bottom than 1 over a million. So this is even closer to 0 than this fraction. And it actually doesn't matter. If you did 1 over a negative 1 million, that would be very close to 0 also, but it would just be slightly negative instead of positive. So same thing here. If you have 1 over infinity or if you have 1 over negative infinity, both of those numbers are very, very, very close to 0. So we're going to finally use that idea that we talked about at the beginning to evaluate this big fraction. So here's what we have. We've gone through and we have taken and substituted in our negative infinities. And if you were to take a look at this number here, it is exactly the number 5. We don't even need to estimate that. It's just 5. But this number right here, we have 2 over negative infinity. That's 2 over a very, very, very big number. That is very close to 0. And we have that in a bunch of different places. The infinity, or negative infinity in this case, that's in the bottom, is being raised to a power, but still, this is 2 over a very big number. That's very close to 0. This is 1 over a super big number. That's really, really close to 0. We have 1 over, again, a number that's super big down in the bottom. So each one of these fractions ends up being really, really close to 0. So what we end up with is basically this in our next step. We have 5 plus something really close to 0, minus something really close to 0, plus something really close to 0 on the top. And in the bottom, 2 plus something close to 0, minus something close to 0. That just gives us the fraction 5/2. We'd want to reduce that down as much as we can, but that is our final answer on this problem.